In this video, we'll discuss the effect of an inductor on voltage in a circuit. And we will explain the convention for how to write the terminals of an inductor and the equation that relates voltage and current. Suppose you have a current I going through an inductor. And suppose you know the current's rate of change, di dt. Now suppose this current decreases. That means that di dt is negative. It means that the change in current is negative or lowering. Now, if the current in the inductor is decreasing, the inductor does not want the current to change, so it will try and force the current to keep going in this direction. To do so, it must exert a force on the particles inside of it. This force pushes the particles from a lower voltage to a higher voltage. That means that if the current is decreasing, there must be a voltage rise in this direction. So this is our sign convention. We write that this top terminal is the positive terminal, and this bottom terminal is the negative terminal, and this is V. Note that this is a voltage drop. So if V is positive, that means that the voltage drops from the positive terminal to the negative terminal. If V is negative, that means the voltage rises from the positive terminal to the negative terminal. So, since we know that if the current is decreasing, the inductor will force a voltage rise in the downward direction, that means that if the current is decreasing, V is going to be negative to represent a voltage rise. Thus, the equation for the voltage across an inductor based on its current is V equals L di dt. These signs are correct as long as you use this convention, where current goes from the positive to the negative terminal. Observe that if di dt is negative, that means the current is decreasing. According to this equation, V will also be negative. If V is negative, then instead of getting a voltage drop from positive to negative, we get a voltage rise from positive to negative. That means the voltage here is higher because particles are being pushed up by the magnetic field to restore the current that we are losing. On the other hand, if the current increases, di dt is positive. If the current increases, the inductor will try and resist the increase in current by pushing particles back in this direction. That is, the inductor will cause this voltage to be higher than this voltage because it's forcing the particles back up, which means that if this voltage is higher than this voltage, there is a voltage rise in this direction and a voltage drop in this direction, which means V must be positive in the case that the current is increasing. This is, I will admit, a pretty strange convention, but it makes sense in a logical way that's not inherently intuitive because of the directions that we've put the terminals. But as long as you connect the positive and negative terminals with the flow of current that you've selected in this manner, this equation will always hold true. Another fact that may be evident from this equation is that if di dt is 0, that is, the current is not changing, there is no voltage drop across the inductor. That means that once the current finishes changing, an inductor basically acts as a short wire. There is no voltage drop and no resistance, so if particles have the choice between traveling through a resistor and an inductor that has no voltage drop across it, particles will always choose the inductor and will always ignore the resistor. Thus, in a circuit which has an inductor but has reached what we call steady state, where the current through the inductor is no longer changing, we should rewrite the circuit as follows. Observe that we have not even drawn the inductor at all. We can now, for all intents and purposes, treat this circuit as having two resistors. If we wanted to find the current through the inductor, we could simply find the current through this branch because the inductor is in this branch. It's just doing basically nothing. So we can model the circuit as not having an inductor at all as long as it's in the steady state. Finally, inductors can be combined in exactly the same way as resistors. Inductors in series add directly together into an equivalent inductor, and inductors in parallel add as the reciprocals of their inductances. One more thing, the energy stored in an inductor, let's call it W, is equal to Li squared, where I is the current going through the inductor. To learn a practical tip about the dangers of using inductors in a circuit, go watch Eugene Kutheriansky's Inductors and Inductance video if you haven't already. His video explains how inductors respond to when a switch turns on or off in a circuit, and the dangers of what might happen if you turn off a switch for an inductor without giving the inductor another space for its particles to flow. You'll understand more when you watch his video. That concludes my lectures on inductors.